when we're doing a Newton's law problem, Newton's laws can only tell us the size of a force or the acceleration of a system. That's all they can tell us. Now, that doesn't mean that your question will be, what is the acceleration or what is the normal force? Your question could be, how far does the object travel? But you have to understand that how far the object travels probably has a lot more to do with, say, things like delta x, vi, v final, a, and t. But Newton's laws will tell you just this piece. Does everybody understand? So when it comes to Newton's laws, although they're powerful, they really only tell you something very limited. So here we go. We're going to do what I feel is one of the simplest questions I can possibly ask you that is, in my estimation, complicated enough to make sense here. Is that where I'm going to start, okay? Now, before I do that, I want to remind you of something. Newton has actually two laws that we're going to use to make this happen, but they're really just one law. Newton was all about this concept of inertia. He believed, and rightly so, because it's been shown that it works great, that forces cause changes in velocity. That's the definition of what a force actually does. Forces cause changes in velocity. At the time when he was making this up, there was no such thing called a force. People knew about pushing and pulling, don't get me wrong, but he tried to quantify it in a way that was unique. And what he said was that if the forces on a system are balanced, then there will be no acceleration. I'm being very careful about how I say that. And I'm not writing all that down. You should write it down. He said, if all the forces on a system are balanced, then there will be no acceleration. This means the natural state of motion is constant velocity. We said that yesterday, just reiterating it. The natural state of motion is constant velocity. So in the universe, if something's moving, it will continue moving forever. Now, we don't see that in our everyday experience, and that's because there are lots of forces that act in our everyday experience on objects, with the most common being things like drag and friction, which are almost always slowing objects down to a stop. That's why we don't see everything in a room moving. But you have to understand something, that we have all these forces that are invisible acting all the time. And it's because of that we tend to see things stopped. But this statement says, when you add up all the forces, if the object isn't accelerating, they must equal zero. This is not an equation. This is a set of instructions. I want to be very clear. People look at this and say it's just an equation. It's a set of instructions. And there's two parts to this set. This is the first. The first is when it's balanced. If you know it's balanced, or you know the object isn't moving, or you know the object's motion isn't changing, then when you add up all the forces, you know they must equal zero. Because if it's not true, if the object is accelerating, then when you add up all the forces, we should be able to predict what the acceleration is. Objects accelerate based on how big they are, how difficult they are to change. Objects that are more difficult to change have more inertia. Objects that are easier to change have less inertia. It's just a coincidence that an object's mass is a measure of its inertia. It's very coincidental. In fact, people have been trying to study why the same thing that causes gravity also causes inertia. I don't care if you know why. I will, however, refer to this as inertial mass. And when we deal with gravity, I will call it gravitational mass, just to help you remember that mass serves two different purposes. It creates gravity, but it also resists changes in motion. That's what the word inertia means. Mass is a measure of how much something will resist a change in motion. So again, this is not an equation, this is a set of instructions. I will never write F equals ma on the board. I will always write this sigma out front as a reminder that our job is to try and identify and add up all of the forces that could be acting on an object. And when we do, we are either going to set it equal to 0 or we're going to set it equal to ma. We will let the situation dictate which one makes the most sense. Now, just a brief aside. If I grab any one of these books off the shelf, the books that are intended for people who are never going to understand physics will have 50 problems that say things like a 200 Newton force acts on a 10 kilogram object. What's its acceleration? A 200 Newton force acts on a 10 kilogram object. What's its acceleration? Do you understand why I really am not interested in doing that? That's not what's happening in the universe. I've assigned like 15 of those. That's your homework. If you've tried your homework, you know that it all says stuff like that. That's mostly me just trying to tell you that's the kind of problem that can be there. That is not what's going to be on your test. Because I don't need 15 of these to help you understand F equals ma, because that's not what we're doing. So, yeah, I think all of you know that this is going to be, 20 meters per second squared. This is mostly an exercise in reminding you that a Newton is a kilogram meter per second squared. That's really all that is. So I can ask that problem 3 different ways. I can say if an object has a mass of 10 kilograms and is accelerating at 20 meters per second squared, what net force is acting on it? 10 times 20 is 200. If an object is experiencing a 200 Newton force and is accelerating at 20 meters per second squared, what's its mass? 10 kilograms. You understand how ridiculous 15 of those questions are now, right? You've done all 3 of those questions. There's nothing else out there. Those aren't real problems. That's what you give middle schoolers to do. Okay? I want to show you what a real problem looks like so you have an understanding. So let's look at a real problem. And here's where your set of instructions really going to come in handy. I'm going to talk about how to analyze a problem like that. So let me explain the problem. This is the problem I use in every single class every year to start this topic up. I have an elevator with people in it. Together, the elevator and the people have a combined mass of 300 kilogram. The elevator is attached to a cable that's going to hoist the elevator to its floor. Okay? Here's the question. The elevator accelerates upwards at 2 meters per second squared until it reaches its cruising speed. How much tension is there in the cable that's holding the elevator? I'll say that all over again so you get the cadence of how one of these problems sounds. An elevator filled with people has a combined mass of 300 kilograms. There is a cable attached to the elevator that is used to hoist the elevator up and down. The elevator is going to accelerate upwards at 2 meters per second squared until it reaches its cruising speed. What is the tension in the cable while the elevator is accelerating? I want you to know at least one piece of outside information that you would have to know to solve that. And that is the force of weight. The force of weight is considered the force of gravity as it acts on an object in a uniform gravitational field. That's one hell of a complicated sounding sentence, isn't it? But it's just how hard gravity pulls on objects near the Earth, or near the moon, or near Mars. Your mass is the same everywhere you go. Your weight is different. Weight is the product of your mass times the acceleration of gravity. That's your weight. So a 300 kilogram elevator would have a weight of 3,000 newtons. Right? Acceleration of gravity near the surface of the Earth is 10. So 300 times 10 would give me 3,000 kilograms meters per second squared, or 3,000 newtons. So whenever you're given something's mass, you can immediately know its weight. Everybody good? That's a piece of information that you need to have for the rest of the year. All right, here's how this problem gets solved. Step 1, you should always ask yourself, what do you think is happening in the problem? So I want to actually describe what I think is happening in the problem. I think the cable is pulling upwards on the elevator. Does that seem realistic? I think because of that upwards pull from the cable, the elevator accelerates upwards. I think the cable has to pull pretty hard on the elevator. But I heard that the elevator was accelerating. So this also makes me think that this is more the law with acceleration and not the law with zero. Does that make sense? When you're asking yourself what you think is happening, you should be trying to decide whether you think this is a second law problem or a first law problem. That's how they're divided. Net force equals 0 is considered Newton's first law. Net force equals ma is considered Newton's second law. When you're trying to deduce what you think the problem is about, you should try and be delineating which one of these is the thing I should go with for this problem. That's what step 1's about. And I think it's this one. Step 2, we're going to create a free body diagram. A free body diagram is relatively straightforward. It's like checking off boxes. It starts with taking your object. Now be careful here. The place that I try to fool you is in trying to manipulate what your perception is of the object. That's why it's hard. That's what can make these things hard. What is the object in this problem? Is it the elevator or the people in the elevator? It's the elevator. I used words like the elevator is filled with people. But what does the cable touch? The people or the elevator? The elevator. So be careful about the problems. We're interested in the cable. The cable is not attached to the people. It's attached to the elevator. So I'm interested in what happens to the elevator. So when you reduce your problem to a dot to start your free body diagram, that dot represents the object. You need to identify what your object is and not become distracted. Contact forces have to touch the object in question, or they can't apply a force to it. So the cable doesn't pull the people up. It pulls the elevator up. I bet it's the floor that pushes the people up. You follow the difference there? I know it sounds subtle, but you get that the subtlety is where I'm going to get you, right? All right, so now our next job is to draw an arrow that represents each of the forces acting in the system. I want to go down the list of all the possible forces that could act. They might not be used. It's a checkbox. The first one is you're going to ask if there's any fundamental forces acting on your system. There always is, because almost every problem we have is going to be near the surface of a planet. The only time you wouldn't say yes, there's gravity is if it's out in the middle of space somewhere. So be prepared every time to start with a downward arrow to indicate gravity. You don't get a whole lot of respect for saying gravity, but at least you know you're participating. When you draw this arrow, you are drawing the scale of the rest of your drawing. So keep the length of this arrow in mind and be moderate. I have to draw it big so everybody can see it, but be careful. The way you do this is to try and anticipate the size of the arrows so you can kind of draw this to scale. So now I'm going to start looking at the contact forces. And the first contact force is the normal force. A normal force occurs when there's ever any two surfaces in contact. Is there any surface in contact with the elevator? Be careful. What's the surface in contact with the elevator? Do I have a floor here? We don't know that it's resting on the floor. Now, I've been on a lot of elevators. Most elevators aren't resting on a floor, but some elevators actually have a pole underneath it and they're pushed up and down. That's how a lot of the mall elevators work. But this elevator you were told had a cable. So I see no floor. And unless you're told about walls, there probably aren't any walls touching it either. And if there were walls here, they could apply a force. But no walls, there's no surface, there's no normal force. This problem has no normal force. The people are experiencing a normal force. But I'm not interested in that force. It acts on the people, not on the elevator. Yes, ma'am?
So the tiny surface of the cable wouldn't count?
No. We assume that the attachment point and all that, that's just a cable. So, no normal forces. Are there any tension forces acting in the system? Yeah, there's a big cable. So I'm going to draw an arrow representing the cable. Would we all agree the cable pulls upwards on the elevator? Now, here's the important thing. When I draw that, should I draw it this big? Would that be the appropriate size? No, this shows an unbalance, but it shows an unbalance downwards. If this were the case, the elevator would be accelerating downwards. Should I draw it the same size? No, because that would suggest that they're the same. I want to draw the upward tension to be greater than the weight because the object accelerates upwards, and this is an upwards force. It doesn't seem unreasonable that this is the thing causing the elevator to accelerate upwards. That's a guess. I am guessing that that's true. I don't know for sure. I haven't done the math yet, but it's not unreasonable. All right, if there's no normal force, there's no friction. You can ignore that. Drag would be the force of an object going through a fluid. You should include drag here, but in practice, we only include drag if we're told to include it. Most of our problems will have little sentences in them like neglect air resistance. That's the sign that you don't have to include drag. And the only other force that we may or may not have talked about yesterday was thrust. Is there like a rocket-powered engine on our elevator? Unlikely. This isn't the Willy Wonka elevator. So I think we're all right. So we have gone through a series of steps, checking off the boxes to indicate which forces we believe might be acting on the elevator. Now that we're done, we get to the actual work. None of this has to do with solving it. This is just a construct to help us. Something that's constructive to help us. Our next step is to add something to our drawing that will help us solve the problem. And this one seems ridiculous, but do not skip this step. Do not minimize its importance. Add a coordinate system to your drawing to identify the x direction versus the y direction. I think it's kind of obvious that I'm going to make my x direction and y direction kind of aligned in a pretty straightforward way. You good with that? Now don't stop there. Label. What is x and what is y? And Be clear about what direction is positive. Also, you will get it wrong if you don't apply labels to your arrows. Make sure you give them a name. I don't care how you name them. You can use the book's convention or mine, but give them a name. Once you have identified your coordinate system, take the law that governs that problem and break it up into two parts, the x direction and the y direction. Hopefully, you've been careful enough so that the acceleration only appears in one of the two directions. My elevator is not accelerating left and right, so the net force in the x direction is 0. My elevator is accelerating up or down, so I place the acceleration in the y direction. Now, in many problems, you'll have stuff here. You'll have forces that are lateral, and you'll have forces that are up and down. This example, though, there's nothing. So the only thing I have to worry about are the forces in the y direction. And there are two forces in the y direction, don't you know? Now look, there's a line here. The right side is what's happening. The left side is what's causing it. I don't know which side of this line you're going to have. Different problems will provide you with different information. We actually know what's happening. A 300 kilogram elevator is accelerating upwards at 2 meters per second squared. We know that that's happening. In fact, I know that this is now 600 newtons. This isn't the answer, but this would be the answer to the question, what is the net force on the elevator? That is the net force on the elevator. It's what happened to the elevator. It's MA. However, the left side is actually the part that tends to be hard for folks. The left side contains the forces that are actually causing this to occur, of which there are two. There's the upwards tension and the downwards weight. So I make the tension explicitly positive, because I said upwards was positive, and I make the weight explicitly negative because the weight was downwards. I'm going to flip to another slide since I'm at the bottom of this one. Is that all right with you guys? So what I'm left with is tension minus weight equals 600 newtons. Moreover, tension minus, what was the weight of the elevator? 3,000 newtons equals 600 newtons. Which means the tension in the cable must be 3,600 newtons. All right. I want to at least piece it together a bit. Again, we were told the elevator is now accelerating downwards at 5 meters per second squared. So, just considering the elevator itself, it's not a big difference, but it suggests that the acceleration has changed. I'm not sure it suggests anything else has changed. So when I consider the forces, the weight's going to be the same arrow. And it's still going to be downwards, but the elevator has to accelerate downwards, meaning the net force on the elevator has to be downwards. The rope doesn't push on the elevator, though. Let's not get that into our mind. The weight of the elevator is still here. The rope, on the other hand, still has to be pulling upwards. So when I draw this, and I know that the net force has to be downwards, It might seem weird, but I'm going to draw the tension as just being smaller. And this isn't a surprise. It is actually the weight of the elevator that slows the elevator down. We just don't pull up as hard on it during that time. So now I say my net force equals MA. I know it's accelerating. I set up a coordinate system that I think will be useful. X, Y. I break this up into the net force in the Y direction and the net force in the X direction. I set this one equal to 0, and I know that this is overkill, but I told you I'm doing everything very thoroughly. This one will equal MA. My net force is still going to be tension minus weight. That hasn't changed. However, it's now M, 300 kilograms, times A, which is -5 meters per second squared. If I said up is positive, the acceleration has to follow the same rules as the force, so if the acceleration's downwards, it's negative. Which means my tension in the rope must be 1,500 newtons, half the weight of the elevator. And that's the right answer. Yes, ma'am. So your 10 kilogram sled is being acted on by a horizontal force of 50 newtons. You notice that the sled slides at a constant velocity. What is the size of all the forces acting on the sled? All right. Does everybody have the problem down? Again, I have a 10 kilogram sled resting on level ground. You pull on the sled with a 50 Newton force. That force is horizontal, meaning it's along the ground. You notice that the sled moves at a constant velocity. What is the size of all the forces acting on the sled? All right, let's begin. Step 1, I want to identify what's happening to the sled. The sled's going at a constant velocity. That means that the acceleration is 0. That sends off alarm bells. Look for that phrase in the problem. If you see that phrase, that means the forces are balanced. All the way balanced. Folks, I would like you to see if you can finish this tonight. There are 4 forces acting on the sled. There's 50 newtons. There's weight, which is 100 newtons. There's normal force, which is 100 newtons. And there's friction, that's 50 newtons. See if you can find the same answers as I. Okay? Try it out.